Hello and welcome back. Today we're going to talk about state functions and enthalpy in regards to chemical energy. So if we are looking at state functions, so most of the time we have no way of knowing your energies in a system, your initial or your internal energies. It's just too complex to go through and figure out all of that. However, we know that the internal energy of a system is independent of the path by which it achieved its state. Meaning, if I have this container here of water, this can become room temperature water by one of two ways. Well, multiple ways, but in this case, two situations. One, I can have boiling water over here that I let sit out and it cools. That's going to get me to room temperature water. Or I can have a block of ice that melts and becomes room temperature water. Because I only know that I have room temperature water when I'm done, and it doesn't matter how it got there, that is considered a state function. And so state functions depend only on, when we say state functions, we're talking it only depends on the present state of your system. That's really important. So state functions only depend on the present state of the system, not how it got there. And so because internal energy is a state function, that means that your delta E depends only on E initial and E final, not the path it takes to go from one to the other, just what you start at and what you end at, and that is going to tell you your internal energy. While internal energy is a state function, Q and W are not. So Q and W are not state functions because whether the battery, in this case, we have a fan running, or a battery running a fan and a battery running through a wire. So whether the battery is shorted out or is discharged by running the fan, delta E is the same. But, so we changed our energy. So our battery lost energy and it ran out. But because in one case, in case B, it's turning a fan. In case A, we're losing it due to heat. Those are totally different. So Q and W are different in both cases. So while delta E can be a state function, Q and W are not state functions. They depend. And so in this case, we have a charged battery that loses some to heat and some to work. In this case, the battery over here lost all of its energy to work, and on this side, so this one lost heat and work because it's running through a wire. We lost it to energy, or to friction, and thermal energy there, but it's all going down. This one lost it because it's running through a fan. There wasn't any discharge due to friction. It was just the work of turning the fan caused the battery to drain. Work. If we have an open container, the only work done on that container is by a gas pushing on the surroundings, or by the surroundings pushing on the gas. So work is here. You either have, if it's open, you have the surroundings either pushing down or the gas pushing on the surroundings. That is going to be your work in that situation here. In this case, we can push down, we can close that. That's the work being done, is you are pushing down on that container. This one, the gas is pushed back and expanded out. And this is going to be your change in volume in those two cases based on the work done by your gases. We can measure the work if your gas, so we can measure work if the gas is done in a vessel that has a piston attached to it. So in this case here, I have a piston, I have gas inside. The gas is going to push and cause this piston to move up. So that change there is the change in volume. So the pressure is applied and the volume changes. So work is equal to negative P delta V, P being pressure, V being volume. In this case here. And to do all this, when we do all this, we're going to talk about enthalpy. And so enthalpy is the internal energy plus the product of the pressure and the volume. So enthalpy is looking at internal energy along with pressure and volume, which is the work. But a process that takes place at constant pressure, and most of what we work with is going to, and the only work done is this pressure, so we change the volume, we can account for heat flow during the process by measuring the enthalpy of the system. So we're looking at the change in heat and where energy moves to. We can measure that with enthalpy. So we can have this equation, which is H, which stands for enthalpy, is equal to your energy plus PV. So that is your enthalpy equation there. We're going to look at this moving forward. So when your system changes at constant pressure, the change in enthalpy, or delta H, is equal to the change in your energy plus PV, which can be written as delta H equals your change in energy plus your P delta V, because volume is what we're changing with our pressure. We're not actually changing the pressure, we're changing the volume, but either way works. You have to have a change somewhere. That's your enthalpy equation. Since E, which is our internal energy, is equal to Q plus W, so E equals Q plus W, W equals negative P delta V, we can substitute everything in and get our enthalpy expression. So delta H equals delta E plus P delta V. We got that on the last slide. I know that P delta V is the same as a negative work because of this. If I move the negative sign, I know that P delta V is the same as a negative work. And that's where we're getting this. I know that E is equal to Q plus W. So for my E, I can substitute Q plus W. P delta V, I can make this a negative W. So delta H equals Q plus W minus W. And so positive W minus W is going to cancel out. You're left with just your enthalpy is equal to your heat change. So at constant pressure, this is where it becomes important. Constant pressure, the change in enthalpy is the heat gained or lost. So at constant pressure, that's this one. That's that equation there. And our last little bit we're going to talk about is endothermic and exothermic. So we talked in the last lesson about endothermic and exothermic versus endergonic and exergonic. Endothermic means you are gaining heat. So if a process is endothermic, that means that delta H is positive. Or if delta H is positive, your process is endothermic. Delta H again is enthalpy, so which refers to heat. Because remember up above we had delta H equals Q. Q is heat. And so if delta H is positive, it means heat is positive, it means you are gaining heat and you're endothermic. If delta H is negative, it means you are losing heat. It means Q is negative, delta H is negative. That's exothermic, losing heat to the surroundings. And so the fast facts, the things that you need to know. 1, enthalpy is an extensive property. If you think clear back, extensive meaning it depends on the amount of substance. The more substance you have, the more enthalpy you have because you have more energy inside of you. Delta H for a reaction in the forward direction. So if we go from A plus B produces AB. This is my forward reaction. Delta H is, in this one, is going to be the same size but opposite direction for this one, A plus B. So delta H in both cases is going to be the same in size, same in magnitude, but opposite in sign or direction. So in this case, if delta H is positive, if this one, delta H, we'll say it's positive 30, then this one, delta H, is going to be negative 30 joules. So that's number 2. And then the last one, delta H for a reaction depends on the state of the products and the state of the reaction. So it depends on state of products and the state of reactants. Those are the 3 kind of fast facts about enthalpy. And that is where we're going to leave off today. So thank you very much for listening, and I will see you guys next time.